I was asked to start with questions, to be fair to the people who are late.
When you have the infalling, like say some sort of collapse that leads to a black hole and it's not necessarily like a shell, do you still have that all the horizon generators are equal?
Yeah, regardless of the nature of the collapse. The fact that a causal horizon is achronal is actually a theorem.
Oh, no, maybe like when I extend the geodesic pattern, there's a reason why I couldn't use the...
Oh, no, the other, okay, sorry. You mean when they leave the horizon?
Yeah,
I don't see any way to get around it.
because it passes through the matter shell, or it won't like, so if you had like some generators and I'm not going through because the collapse is...
Well, it's just that, you know, once it's outside the horizon, you could just intersect it a long time in the past and then take your time and then jump in the horizon later. Are there any other questions while people settle in? I guess oh yes?
The wall entropy, does it satisfy second law?
In general and non-linearly, the answer is probably no. There was a paper I wrote about how you can prove that the Dong entropy, or something that agrees with the Dong entropy for f of Riemann gravity, where you calculate it, obeys the second law for first-order perturbations to a killing horizon. So for first-order perturbations to a killing horizon, you could get a second law for pretty much for any matter scalar action you make up with any number of derivatives, any metric scalar action, at least. But at nonlinear order, if you do something like Lovelock gravity, there are sort of counterexamples where if you merge two black holes, the entropy goes down.
Isn't that slightly disturbing?
It presumably means that it's not consistent to just add a Lovelock term all by itself without it being part of a bigger set of things with other effects coming from either quantum or stringy corrections, as the Chems paper argued using causality. Okay. So we were discussing before we were so rudely interrupted by my time running out, the generalized entropy as a proposal for the entropy of the black hole. And just to remind you, this takes the form of the leading order piece looks like the area. And then can be, if you have additional corrections to your gravitational action, you can have additional correction terms. For example, if you have a non-minimal coupling term in your action, this will actually get you something that's proportional to, there might be some pi's in here or something, but I won't worry about that. It'll give you something that's proportional to the integral of phi squared on the horizon. And if you had something like an r squared term in the action, you would get something related to the integral of r. So on the horizon. And then all of these are collectively the generalized area. And then there's this other term that comes from the matter that I'm calling S out. And these things all depend on your RG cutoff. So Newton's constant will depend on epsilon. And if you have some coefficient in front of this will depend on epsilon. In some theories, xi may depend on epsilon, although not in this free case. And so the statement, and the S out depends on epsilon. So we have various terms that depend on your cutoff, and the idea is that this quantity is preserved under renormalization. So if I flow from the ultraviolet to the infrared, typically I'd expect my entropy is positive, because a good entropy should be positive. So as I go from the UV to the IR, I would pull things out of this term, and the leading order area law divergence would go into this term and shift 1 over g, but I might have a sub-leading term, for example, that goes into this term. And there can also be RG flows within this area of the generalized entropy. For example, phi squared is something that requires point splitting to make it well defined, or some other regulator. So this really has a function of epsilon as well, and if you renormalize it, that'll go into 1 over g as well, which is why, at least if you calculate using the heat kernel regulator, you find that the shift of 1 over g actually is proportional to 1/6 minus xi, where 1/6 is the piece that comes from S out, and then there's this other piece that comes from xi. The point is, this is independent of the RG flow. The sum is independent of epsilon. Now, there's two very different regimes where we can consider this independence. We can go to semi-classical gravity, where the independence is something we can actually calculate and check and see that it's true, or we could be wild and say, what's this telling us about quantum gravity, and go all the way to the Planck scale. So let's be wild. So there's this hypothesis that black hole entropy just is entanglement entropy, and this is related to something that you probably haven't heard of called the induced gravity scenario. And this part's speculation, although I think that there's evidence from things like ADS-CFT as well as what I'm going to tell you. But I guess you don't have... Questions like, what does the Bekenstein-Hawking entropy count? These are the sorts of things that people famously argue over. Does it just count the stuff out, degrees of freedom outside? Does it also count things inside? Just like people argued about whether the information is lost. So I'm going to tell you what I believe, but you don't necessarily have to agree with me. So, okay, but the sort of core conviction that a lot of people have is that black hole entropy is statistical. That is, it's not just a big fat coincidence that black holes obey the same laws of thermodynamics as any ordinary system. They should, in some sense, obey the same laws of thermodynamics for the same reasons, broadly conceived. And that means that if the entropy of an ordinary system, like a lump of coal, calculates the number of microstates, we would think that the entropy of the black hole should also calculate the number of microstates. Now, this means it must count some degrees of freedom. From this perspective, this term looks good. It looks like something that's a von Neumann entropy that has entropy in its name, whereas these terms look like some sort of coarse-grained thermodynamic description that's really just some measure, should ultimately be some measure of degrees of freedom we don't know about yet. And we see as we RG flowed from the UV to the IR, we took things out of this term. So we might wonder, going the other direction, whether it could be that if we flow all the way to the Planck scale, we'll discover it's all this term. That really is just a von Neumann entropy. One thing that makes that plausible is that if we calculate the value of the entanglement entropy in quantum field theory, we know, as other lecturers have said, that there's an area law divergence, and the leading order area law divergence is a over epsilon to the d minus 2 in d greater than 2, plus there's some subleading stuff. So that's true in field theory, but to go beyond field theory, we can just wildly guess that epsilon is L Planck. That we have some true cutoff that doesn't really make sense to talk about distances smaller than the Planck scale, because then the fluctuations in the geometry are as big as the geometry itself, and at least we don't know what we're even talking about when we talk about rulers or clocks anymore. So it's at least plausible that quantum gravity, there's something unsatisfying about all the cutoffs we have in quantum field theory, where you either, put some artificial truncation of modes, or invent new fields with negative probability, or break Lorentz invariance, or some other horrible thing. But if the black hole entropy is finite, that's really telling you there's some cutoff on the universe that is quantum gravity that is somehow perfectly satisfactory and physical in every way except that we don't understand it. So with this hypothesis, and this is just dimensional analysis here, so we're not going to explain the 4 there, but what we find is that this is A to the L Planck to the d minus 2, which is indeed, this is the same thing as GH bar. So you cover something of the order of the Bekenstein-Hawking entropy. So this was proposed by Raphael Sorkin, that black hole entropy just is entanglement entropy. And that implies, if it's all S out, then there's none of this. And that implies, conversely, that at the Planck scale, A gen equals 0. Okay. Now, it's interesting to think about this a little more precisely using the RG flow. Where we want to work out a beta function. And usually the thing you do when you're doing RG flows is you define a quantity, you use the cutoff to define dimensionless quantities, so your RG flow equation is homogeneous. So the quantity we're interested in is actually 1 over G is the thing that receives additive corrections. So I can define a G to the minus 1 twiddle as epsilon to the d minus 2 over G, where epsilon is my cutoff. And now I can have an RG flow where I say that the derivative of this G to the minus 1 twiddle with respect to my RG time, which you take to be the logarithm of the cutoff. So if you remember your quantum field theory, the first term is the classical term that comes from the engineering dimensions. This doesn't show up in the beta function of QED or QCD in 4 dimensions because the coupling constant is dimensionless. Here, Newton's constant has dimensions, so we get a term d minus 2 to the g twiddle to the minus 1. So if we just had this term, what we would get, as I plot this from the IR, which is known, to the UV, which is not known, which means that this axis is actually minus log epsilon, so I'm doing it all backwards. This is given by an exponential. It's really a power law, but we're writing it in log space, where the value of G, this is traditional labeled over here, the value of G twiddle to the minus 1 goes exponentially. So this is just saying in the IR, Newton's constant is small, which means space-time is more or less flat, hard to modify. As we get to short distances, Newton's constant is large, effectively compared to the cutoff, and therefore it's very easy to have fluctuation of space-time, and we're in the quantum gravity regime. So the quantum gravity regime is when this is small. But there are quantum corrections. These quantum corrections come from the fact that we have this entropic term, and although there's some subtleties coming from things involving edge modes and other terms that may make the Newton's constant anti-screening, if we focus on this term where the entropy is positive, we'll expect there to be a positive contribution from the entropy. So we have a plus C here where C is greater than 0, where C will be something that gets bigger the more and more species we have. So it may also be a function of epsilon if some fields have mass, but let's just treat the number of species as constant for simplicity. Then what happens is that this exponential just gets shifted. There's a fixed point that is at a different value of the 1 over g. And for positive C, this fixed point actually is at negative values of the Newton constant. So that's a little strange, but it means that the equations go like the shifted equation is just a translated exponential. And what that tells you is that there's going to be a point in this RG space where 1 over g equals 0.
We can't really trust the equations of this.
No, we cannot. Plus something that we'll get. But we aren't really, this is just an inspirational idea. I'll mention how this might work in string theory in a moment. The point is, what you can say from dimensional analysis is that you expect that when it gets close to being 1 over g gets close to being 0, that this is going to happen somewhere around the Planck scale. You might wonder, what if I took the number of species to be really, really large? Then I could make it so that this thing is going to actually happen at something much sooner than at a larger distance scale than my naively calculated Planck scale. But the whole point is that these fields are contributing to the normalization of Newton's constant. So the true Planck scale, as opposed to the naive Planck scale, is actually defined as wherever this thing gets 1 over g gets to be small. So that tells you that, in a way, this is, you can't mess up this sort of renormalization relationship. You can't mess up this hypothesis that black hole entropy is statistical just by having large numbers of species, because the RG flow just already knows about that. Yes?
I have a couple questions. So, C, you motivated from how, but is it like a loop correction to the graviton propagator or something like that? Or?
The graviton would be one of the fields that contributes to C.
No, but if I would, let's say I didn't know anything about black hole entropy,
Yeah.
I'm just doing quantum field
Yeah.
to figure out the beta function.
Yeah.
Where is C coming from that language? It's just the usual loop corrections?
It's just the usual loop corrections. One way to put it is that even if you don't know that the metric is dynamical, you can still use quantum field theory to calculate the sensitivity of the partition function to changing the metric. So the loop corrections include things like corrections to the Einstein-Hilbert term and other things.
Okay, but I could just do a regular beta function in perturbative quantum gravity.
You can do a regular beta function. The only thing is it's a beta function that's detecting the sensitivity to the geometry. So if you were just a field theorist who was just living in flat Minkowski space, you might never think to calculate that particular beta function, but it's there. And it's actually the same as the entanglement entropy divergence, so a modern quantum field theory person would still calculate it.
And when you do the calculation from that point of view, is it also clear that C is positive?
Well, so if C is not positive, then it looks like this von Neumann entropy is negative and we're in trouble. There's some subtleties that happen when we're talking about things like non-minimally coupled scalar fields and gauge fields and other things. I personally, I think that these subtleties, except for maybe the ones involving gravitons, have now all been resolved with saying that, for example, in the case of gauge fields, I believe if you use a regulator for the gauge field like a lattice, which makes it clear that the entanglement entropy you're calculating really is statistical, then you will find that in that regulator, in a statistical regulator, C is always going to end up being positive. But because, as you told everybody, the area law divergence depends on your regulator scheme. In a scheme that is less obviously related to von Neumann entropy, it might end up being negative. And people use this sort of scheme all the time, and then you get confused when you think about this topic.
Okay, I have another question.
Yes.
So the way you drew the plot, I think is a little confusing, because in the IR, isn't it the slope that got adjusted by C? Because aren't they all starting at the same point? In the IR, like it's whatever we measure G Newton to 1 over G Newton to be.
That's right. So if you like, I should probably have shifted it horizontally instead of vertically. Yeah. Fair enough. I could make them all agree at one particular point, and then
So
it would look differently.
Because you added a constant to the slope, I think.
Yes. So maybe that, well, we could just say I haven't done it yet, but I'll pretend. I really was doing it over there, you see.
Am I allowed to ask a third question?
10 words or less? That's
How should I think about, does the area change? I mean, you let G Newton flow, but is the geometry independent of epsilon, or what?
The geometry is not independent of it. The dependence of the entropy on geometrical things will be encapsulated in the subleading term. And if it's true that black hole entropy is statistical, we need not just the 1 over G to go to 0. We actually need things like this alpha to go to 0 and this C to go to 0, and anything that involves gravity has to go to 0. And that's actually a good transition to say that this is an idea that was thought of before people got interested in black holes and their entropy. This is something called the induced gravity scenario. So this was an idea of a guy named Sakharov who said that what if there is no Einstein-Hilbert term, there's just some short distance cutoff on the fields, and we just have a matter action, and the matter action has loops, and the loops, when we regulate them, automatically lead to an Einstein-Hilbert term that flows in the IR, and that maybe this sort of explains gravity. Now, it explains gravity in the sense that we're starting at the universe where G is infinity, not that we're starting in a universe where G is 0. So it's a very peculiar universe that you might have thought doesn't make sense. This sounds like a wild, crazy idea. I think it's worth pointing out that's the same as Ted Jacobson and others have pointed out. This is really the same idea that is now conventional wisdom, that all black hole entropy is entirely statistical, but phrased in a more mind-blowing way. And as long as we're speculating about this, there's also a speculation by Susskind and Uglum that there is a sense in which string theory is such an induced gravity theory. So this just sort of involves picture thinking because it's hard to actually calculate entanglement entropy in string theory without going off shell, which is hard in string theory. But at least arguably, in string theory, remember what we do is we have an expansion over string world sheets. So our perturbative expansion involves a sphere plus a torus plus higher genus surfaces. And string theory we know does cut off ultraviolet problems. So at one level, we have the sort of necessary condition for this to make sense. And as you know, when you do string theory, you calculate the action of the string world sheet, and it's not the string world sheet action plus an additional action for the space-time that you add that's some sort of bare gravity term. That doesn't work. It's the action itself comes from the strings propagating in the background. You don't get a choice. It's induced by the string world sheet action to just be whatever combination of curvature things it is. And when you now, this is an expansion in the string coupling constant, where you're the way you implement that in string theory is with a Euler. You use the Euler number of these strings. So there's a coefficient in the action that looks like minus log times the string coupling constant times the Euler number of this guy, which has the strange feature that it's actually this, the g to the 0, and this is g to the 2. This guy's actually g to the minus 2. So it's actually divergent. It's a Laurent series. And what Susskind and Uglum said is if we look at this leading order diagram, and we imagine we were calculating some sort of entanglement entropy with, let's say, the infinite mass limit of a black hole, which may as well just be Rindler space. So if we imagine this diagram is just intersected by some sort of surface of given area, well, this sphere could appear anywhere along that surface, so we'll get something proportional to the area in the entropy. And it'll also be over g squared. And if you work it out, little g squared is the same as big G. So plausibly, you get the Bekenstein-Hawking entropy from the leading order spherical term in string theory, where if you were doing some sort of replica trick calculation, you would actually be interpreting this as open strings that begin and end on the black hole horizon, whose count, so there's a lot of these because this has leading order amplitude, and somehow even in weakly coupled string theory knows that there ought to be something that looks like the Bekenstein-Hawking entropy. Now doing this calculation properly is very difficult, which is why nobody's really done it. But it's too beautiful of an idea not to mention. Yes?
So what happens if you also have open strings? Then you have things that will compensate 1 over g with the fractional power of g?
Yeah, so there might be a g to the minus 1, and then that would be some sort of it seems like that would be some sort of subleading contribution to the black hole entropy. That would be interesting to think about. Of course, all of these terms contribute subleadingly. You can actually also look at this term, and then this looks like a sort of loop correction that gives you the S out correction from gauge fields. And you can even consider cases where it intersects weirdly like that, and that actually corresponds to the edge modes of the gauge field. And somehow, string theory knows that the positive and negative contributions of all of these higher spin fields, the excitations of the string, somehow all cancel out to give a finite answer without any divergences left over. But it's the usual ways people look at string theory with all these ghosts and so on aren't really useful for getting a statistical understanding. Yes?
For the induced gravity, is it natural that the major contribution is from Einstein-Hilbert rather than other?
Yes, it's natural in the sense that although the loop corrections will generate all possible terms in the action, the dominant one in the IR is going to be the Einstein-Hilbert term. Now, when I say the dominant one in the IR, I'm assuming you've already solved the cosmological constant problem, which is even more dominant, but that's par for the course. That assuming you have set the cosmological constant to be small, the Einstein-Hilbert term is the next most leading term. Yes? It's a good question, but you could say whatever you believe is going on at the Planck scale, and there may be, membrane degrees of freedom, surface degrees of freedom on the horizon, it seems natural to believe that they should be counted in the von Neumann entropy of the things outside. So really the only tricky part is the question of whether it's really reasonable to only calculate the entropy of stuff outside the horizon and on the horizon, and then say somehow you're calculating the statistical mechanics of the whole black hole system. This is, again, the question of what does the Bekenstein-Hawking entropy count, but at least, this is what people do to get the entropy, so it's sort of the same problem, the same leap of faith we always had in black hole thermodynamics. Yes, in the back.
So if I'm not in the UV, we know that the divergence in the area term cancel out the divergence in the entanglement entropy. So why should we associate the state time for black hole with the divergence in the UV just because the area term goes to zero? Like if I do it step by step, there is no area divergence in the entanglement entropy, right? Cancel out by whatever is in the area term. So why? Because you said over there that S out has this area over epsilon to the minus 2 term, and you replace epsilon with alpha.
If you think about it the other way, if there's no area term in the UV, and then we have quantum fields outside, they will generate an area term that should be area over L Planck to the whatever.
But if I'm going to the UV, so any step before that, there was no divergence term, right? The area term cancels out.
The area term absorbs it, but when we talk about the generalized entropy, we're playing it. So one reason to add counter terms is just to get rid of the problem, to say, I just want the divergences to go away and never think about them again. That's the sort of naive approach to quantum field theory. But the Wilsonian approach is to say, no, I care about these things because they're telling me something about the RG flow. They encode some physically relevant information. And it's the Wilsonian approach that we're doing here. And in that approach, we don't regard these divergences, we regard this quantity as we aren't just interested in the supposedly universal pieces like the log divergence because we're interpreting S-gen as a physically meaningful quantity. Since it's finite, we're allowed to do that. Yes?
So if I take this induced gravity thing seriously, and then I want to use, I'm free to choose my scale epsilon at which I want to work. So let me choose to work it at the one where 1 over g nu is 0.
Which presumably corresponds to the objective true cutoff.
Okay, good. So then, is there a black hole? And what does it look like?
Presumably it's a black hole that has this raises this firewalls question, of course, but if we assume it's a black hole, there's no bare term in the Bekenstein-Hawking entropy. It's something that's the entropy is entirely due to matter contributions outside of it.
But it still looks like a black hole.
Well, I mean, we're at the Planck scale, so who knows what's really going on. If something like ER equals EPR is true, then maybe the only reason why the outside of the horizon was connected to the inside of the horizon in the first place is somehow because of entanglement. That somehow that's what we really mean by geometry, is the short distance entanglement. The wild speculation.
But I think
Yes.
the discussion makes it clear that in order to check an idea like this, we need the theory beyond Einstein gravity. There should be some.
Absolutely, and you should definitely not take this part seriously. You need, once you get here, you need a UV completion of your theory. That's what this is pointing, and that's why this idea will always be a little unsatisfactory unless you understand your UV completion. But it's a pointer. Now, this was supposed to be the end of the last lecture. We could all end on this buoyant note of speculation, but I want to get back to Earth and start talking about things that can actually be shown now. So, unless there are well, no, even if there's, I'm just gonna. Yeah. Okay. Let's talk about dynamics of horizons. Because last time I was talking about, we were discussing killing horizons, and you can get a good understanding of the 0th law, temperature is constant for killing horizons, and the first law you can compare nearly killing horizons. But if we want to talk about things like the second law, we're really talking about dynamical questions, and we want to discuss black holes that are growing with time. So the bad news is for dynamical horizons, there is no killing horizon, because if matter is falling across into the black hole, there's just no time translation symmetry. So the killing horizon is gone. Instead, we have some different notions of horizons that in the stationary case, they're all degenerate and they agree with the killing horizon. But in general, they differ from each other and are and so there's a question of what is our definition of our horizon that should obey a second law. But there's multiple rival candidates. So one definition is the event horizon. And that says it's defined as the boundary, going to do that with this partial notation, the boundary of the past. This is the sort of Penrose and Hawking notation. I minus means the set of all points to the past of some points to time-like past, of scri plus, which means future null infinity. Okay, so this is the definition of the event horizon, but it assumes that there is a future null infinity, that we have some sort of asymptotically flat or ADS case, and there's a better definition, which is, the better definition is a causal horizon, where the causal horizon is defined, actually I'll call this the causal horizon C plus is defined as the boundary of the past of L, where L is any locus of points at future infinity. So this is related to a definition originally given by Jacobson and Parentani, where they said a causal horizon is the boundary of the past of any future infinite world line. A future infinite world line goes to some point at future infinity. I'm telling you that we can generalize this and take any set of points at future infinity. This is often useful when we're doing ADS-CFT because we're often interested in things like domains of dependence on the boundary that don't necessarily have one maximal future point.
So future infinity here is the ADS boundary?
That's correct, because there are world lines that go off to infinity forever to the future that hit some point at a finite point on the. So this is, so for example, when you do this thing where you have a domain of dependence on the boundary and then you take the causal wedge, which is the intersection of the past and future of this thing, by this definition, this is a future causal horizon, this would be a past causal horizon. The plus means future, and I won't say this explicitly except now, but you can of course time reverse all of these definitions to get the past versions. So this definition of a causal horizon as opposed to an event horizon is good because we can now apply to other cases like de Sitter or nearly de Sitter, where we have, or maybe I'll just call this cosmology or some DS-like, where we have causal horizons that, cosmological horizons that come down in the Penrose diagram like this, or we have Rindler horizons, the boundary of the past of some accelerating world line. We can, all of these things seem to obey the same laws of thermodynamics as whether it's a cosmological horizon or a de Sitter or Rindler or so on, which makes it deeply dubious if we give a different answer about firewalls in these cases, but everybody is horribly confused about that topic and there are no good answers. So as I hope Ahmed satisfactorily showed you. So the causal horizon obeys an area law, as Edward already showed you, and so I'm not going to replicate it, but it involves, crucially, looking, I'll remind you that it looks at this expansion that you can define as the rate of change of the area of an infinitesimal area element per area. This is not how he wrote it, but it's equivalent to what he said. And the statement is that for a causal horizon, this is greater than or equal to 0. And this comes from the null energy condition plus the Ray-Chuduri equation, theta dot equals minus theta squared over d minus 2 minus, there's a shear term, minus RVV. So this stuff's all negative. And the null energy condition is used to say this is negative. Okay, so this is not the only notion of a horizon that people use. There is another notion of a horizon which is called has several names, but it's the other main candidate, Sean Hayward called it a trapping horizon. It's also called sometimes a holographic screen, and in the special case where it's space-like, it can be called a dynamical horizon, but that's very confusing because it prevents me from naming the section dynamical horizons. So the future trapping horizon T plus is defined as a codimension 1 surface that is foliated by codimension 2 leaves, which are marginally trapped, which means that one of the null directions, the outward one, let's say, is 0. By theta v, I mean you vary the area in the v null direction. And when I say theta u, I mean vary it in the other null direction. So theta u is going to be less than 0. Okay, so it's marginally, the area is marginally stationary in this direction, and it's decreasing in this direction, which makes sense if this is a black hole. This is closely related to the idea, the leaves of this thing are closely related to the idea of an apparent horizon, which has a number of inconsistent definitions of the literature, but is sometimes defined as the outermost marginally trapped surface on a particular Cauchy slice. That definition is often imposed to make sure that you have the case of a black hole rather than the sorts of things that happen in Minkowski space. Ideologically, I'm opposed to that because I want to also discuss Rindler and all of these other cases. So I'm not going to impose that. But it frequently is imposed by people who want a criterion for does a black hole exist. Whereas I want to understand everywhere and everywhen, and even when there's no black hole.
What was the criteria?
That it's a closed surface. So that would rule out something like the Rindler version of a trapped surface or the ADS-CFT version of a trapping surface. But it's also important for it to be closed if you want to do the Penrose singularity theorem. Yeah. But for purposes of a second law, we don't require that. Now, if a horizon is non-compact, well, you know this, but everyone may not. If a horizon is non-compact, we are just interested in whether there's local entropy increase on the horizon. It doesn't matter if there's a flux at infinity. Was there a question over there?
Yeah.
Yes?
In each case of a dynamical horizon, do you use some transformation to define the temperature?
So horizon, in these talks, I'm only going to define temperature in equilibrium, which is as good as I think one has a right to expect. However, specifically for the notion of the trapping horizon, there is actually a generalization of the surface gravity that you can use to define a sort of local temperature in that case. It exists, but I'm not going, and it comes into the fact that these trapping horizons actually obey a local form of the first law instead of a sort of global one.
What is the local?
It just means that there's something like dE equals TdS, where the d's are interpreted as local fluxes at one point, instead of the first law I showed you last time, where it's interpreted as the evolution of the black hole all the way from minus infinity to plus infinity. So, but at the moment I'm interested in the second law, where I'd like to see it. This is a local second law for the causal horizon. The horizon itself is not defined locally. The causal horizon is teleological. Which is a fancy word for saying that by definition it depends on what's going to happen in the future. So it looks like it behaves acausally based on what's going to fall into the black hole in the future, but it's just an acausality in the definition, not in the physics. This people like because you don't have to look at the future, to see that you have a marginally trapped surface, but it has its own ambiguities that it's not unique in general. Except with spherical symmetry. If we impose spherical symmetry in like Schwarzschild, then it's unique. But in general, we could take any foliation of a black hole with Cauchy horizons, find the outermost trapped surface on each of those. We get a trapping horizon, but which one we get will depend on our original choice of foliation. Yes?
Do different local observers agree on predictions of these laws?
Well, the laws are always asserting something about what's happening on the horizon. But, I mean, everyone is agreed on the equations of motion that solve the full d-dimensional space-time. We're just analyzing different surfaces that have different properties in that space-time.
But you do this locally, so is there, do you need some kind of a notion of parallel transport to
Well, I mean, that's when we talk about area increasing locally, we're differentiating the area, so that's using parallel transport implicitly. Yes?
So let's say we just have Schwarzschild, eternal Schwarzschild. Does that have various future trapping horizons besides the opposite?
Well, in eternal Schwarzschild, it's killing. So the trapping horizon, the causal horizon, and the killing horizon all coincide.
Are there other trapping horizons in that spacetime? If we don't impose spherical symmetry on the surface?
I believe there are not. Or I believe in that special case it's foliation independent, but in general it's not so much. Because for any Cauchy slice, whatever cut of the horizon you reach, it's marginally trapped at that point. I think it's sort of all degenerate and then sort of spreads out as you add matter. Yes?
So for alternate radiation, it's heaven at trapping horizon or outside of horizon?
That's really not the sort of question that I think has a meaningful answer. Remember that every codimension 2 surface has the property that every codimension 2 surface has the property that if you zoom in, it looks like Rindler at short distance scales and you have the Unruh effect. So all of these things are in some sense quantum mechanically firm. On the other hand, let me draw how this looks with a black hole that forms from collapse. Because there's a sense in which the answer is the causal horizon. So here's the black hole that forms from collapse. It's causal, so there's some star here. Okay? And the causal horizon will always go at 45 degrees in the Penrose horizon. In the Penrose diagram. So this is C+. But the trapping horizon can actually be time-like or space-like. Now, it's always foliated by leaves that are marginal in the null direction, but that may poke away from the surface. In fact, it can have segments that go time-like to the past, and it can have segments that go space-like outwards. And when there's no matter falling across, it can be degenerate and go null. So this is a trapping horizon, and it's foliated by marginally trapped surfaces going this way. This is a spherically symmetric example, so it's unambiguous if we impose spherical symmetry where the trapping horizon is. Now, the Hawking radiation comes out here. You remember that Edward proved that the marginally trapped surfaces are always behind the causal horizon. So by causality, there's certainly, if you define the Hawking radiation as people usually do, by what gets out to infinity, then there's indeed a sense in which that's, if we trace that back here, it's associated with the causal horizon instead of the trapping horizon. But you shouldn't, locally, there's an Unruh temperature everywhere. So you want to be careful relating global features of the space-time to local ones. Okay, So what I wanted to say is that the trapping horizon, t plus, can go time-like backwards, and it can go space-like outwards. And it can actually flip back and forth between leaves. At some point, there's a transition here where this thing is null. And it can go back and forth, but always in a way where the area monotonically increases as we go through here. This was shown by Hayward on the leaves of constant signature and by Busso and Engelhardt when we glue together the mixed signature pieces. So just to give a little bit of an intuition for this,
So increasing, we're going in the outward direction. You have, like, looking at an orientation,
yes.
the V direction, I guess, kind of.
Yeah, so the V direction is always this way. And the V is outwards and U is inwards, going to the future.
And when you say increases, you mean in the outward direction, which is not necessarily the future.
It increases going along this way, and then it's degenerate going that way. And you can never glue them together in such a way that it has a wrong junction where it's increasing inwards in both sides or outwards in both sides. And just to give a little bit of intuition for this, to see why this is the case, this does use the null energy condition. So this also obeys second law. But the proof from the null energy condition is a little more local. The way to see this is that, so these guys, when it's time-like, it's called an outer trapped surface because it satisfies, for simplicity, I'm just going to assume we have spherical symmetry. So I'm just going to give a very intuitive and not worry too much about how to make this perfectly covariant in d dimensions. The outer condition says that, actually, I think I'm going to put this elsewhere. All right. So in the time-like case, or the outer condition says that theta v comma u is negative, and that is the case that it's on the, if you imagine that the null surfaces outside are expanding, but as we go in the u direction, it starts to become, let's imagine we're at constant v and we go in the null direction. The first one we hit is going to be an outer trapping horizon, meaning that theta v comma u is negative. And when theta v comma u is negative, we can then use the fact from the null energy condition, we know that theta v comma v is also negative.
So what is theta v comma v?
So we're assuming spherical symmetry, and so I'm just treating the area as if it's a scalar field in 1 + 1 dimensions.
So you just mean the second derivative?
I just mean the second derivative. I could have said area, and then I guess we've pulled the, it would be a second. So the v comma u is really the same as the u comma v. Yes. The point is the Ricciarduri equation says that this thing is negative if we have the null energy condition. And so these two things that say that using these two signs, we can deduce that it's space-like. Whereas if we have an inner horizon that has theta v comma u is positive, but theta v comma v is still negative, then we deduce that it's time-like. And this is just because we've got our two directions. If we just solve for theta v comma u, then by comparing these two signs of the derivative, we'll know whether the locus of points with theta v equals 0 is going in a space-like direction or whether it's going in a time-like direction. Does that make sense? Because a time-like vector is a positive linear combination of u and v, whereas a space-like vector is a combination of the u and v vectors that has a relative negative sign. Yes?
How can this inner and outer horizon connect to each other smoothly?
They do, it depends on what you mean by smooth, because the signature changes as you do this, but they do connect to each other in I think as a function of x and t, I think it's typically smooth. It goes through a case, of course, where this is equal to 0 and it's light-like. That's this point right here. Although, to give credit to what Raphael and Netta did, I should say that it's in general, the transition between the two signatures does not have to happen on a single leaf when you go beyond spherical symmetry. You can have leaves, some parts of which are space-like and some parts of which are time-like, which is considerably more complicated. Okay, so once you know this, then the area law part is actually easy. So if we look at this diagram, I'll blow this up a bit, like this. So on the space-like piece, if we imagine varying a little bit in the v direction, it's marginal in that direction. So if I take a baby step this way, the area stays the same. Whereas if I take a baby step this way, since theta u is always negative, the area is growing. Because the area is decreasing as we go to up and to the left, and therefore it's increasing as we go down and to the right. On the other hand, if I'm up here on this time-like segment, and I take a baby step this way, the area is marginal this way, but the area is decreasing as I go back along the u direction. And so the area decreases going that way, which means it increases going this way. So at least in this spherically symmetric context, you can see that there is an area increase theorem, and it goes in a consistent direction. That raises the question that you could say, which of these area theorems is the one that's really correct and is the sort of fundamental thing that's telling us about black holes, and which one is the imposter that people should stop working on? Well, that's a way of framing the discussion to cause more heat than light, and because ultimately both of these are geometrical truths, and in my opinion, everything that's true needs to end up having some sort of, every nice statement about areas increasing should have some nice quantum gravity explanation at the end of the day. But what we can say is, what happens when we now consider the quantum corrections? Do both of these horizons continue to obey a second law in the form of a generalized second law when I consider area plus the outside entropy? That's the next topic. So are there any comments about this classical setup? Yes?
So it seems like one pretty important difference between these two concepts is that, maybe I misunderstood, but the causal horizon is some hypersurface, whereas the trapping horizon is more like a collection of codimension 2 surfaces. In other words,
It has a privileged foliation.
Yeah.
That's correct.
So is that enter into the discussion of which one is more fundamental or something? I mean, that seems like a pretty big difference.
It is a pretty big, and actually, this is a nice way of answering your question about, it's nicely connected to your previous question, which I'll, I guess, say instead of answering your current question, that if you imagine the killing horizon is a trapping horizon regardless of its foliation, but because in general the trapping horizon is foliation dependent, that's why there had to be multiple trapping horizons. Because for any foliation of the killing horizon you picked, it'll pop off into some trapping horizon once you turn on the matter. Okay. Yes?
Is that theta BB smaller than equal to 0, or is that a strict inequality?
This is a, well, okay. Generic, let's make it a, if we impose the null generic condition, then this becomes a strict inequality, and we can deduce the thing I said about space-like and time-like curves. If we allow, in general, you can have degenerate cases where this ends up being equal, and then that could correspond, for example, if the black hole settles down and there's no mass entering it after that period of time, then it may just be null at that point. So to deduce the space-like or time-like, I should really use the strict inequality. But in the case where it's an equality, I think you just discover that it's null, but the area, in that case, the area is constant. Other questions? Okay. Oh, wait.
Is there an example of one of these generalized horizons where the area is a statistical entropy in some string model?
Well, so usually in most black hole state counting problems, people are considering stationary black holes. A lot of this question about the generalized second law, I mean, these really, morally, as Matt said, the holographic entanglement entropy is the fine-grained entropy. If you really believe information isn't lost, any one of these codimension 1 horizons where entropy is increasing should represent a coarse-grained entropy. So there's a prior question, which is what coarse graining are you using, which should be answered. If you really want a microscopic model, you'd need to impose your coarse graining explicitly. Somehow semi-classical or classical gravity already knows that there's the coarse graining and just does it for you. Okay, let's talk about the generalized second law. All right, so we'll start with the GSL for causal horizons. So, as I said last time, we're going to be making a semi-classical expansion in this sort of thing, where GAB, we start with a background piece, and then we're going to be imposing some sort of correction. There's this graviton piece, and then this piece that's sourced by matter, and it's most interesting to assume that things are trivial at this order, because otherwise the classical order will dominate and the quantum effects won't be interesting. So we're going to do that with this generalized second law. What we want to show is that the v derivative, the functional derivative of the generalized entropy is greater than or equal to 0. And in fact, if we imagine the black hole horizon as something with many horizon generators, it's nicest if we can show that the entropy increases between any slice, no matter how wiggly. So we don't just have to take flat slices. So this can be shown. And one of the tools for showing it is the Ricciarduri equation. So we're going to take the Ricciarduri equation. Let's ignore gravitons for the time being, although you can include them if you want. But we're just going to linearize the Ricciarduri equation, and it's going to give us the theta dot is equal to minus 8 pi g TVV. Okay? We can integrate this. If we integrate it the first time, we get theta of v equals the integral from infinity to v of TVV dv. And if we integrate it a second time, we get something involving the areas. Actually, now I'm going to integrate it in both the v direction and in the transverse direction. I'm going to get that the area at this at any one of these v equals v star slices over 4g h bar is going to, go put it over here. The area at v star equals the area at plus infinity. There's a term, we're going to assume when we integrate this, that theta at v equals plus infinity is equal to 0. This is reasonable when you have a causal horizon because, well, first of all, if no matter falls across the black hole at late times, then it settles down into a stationary horizon and we have theta equals 0. But actually, it's better than that because this v coordinate, in the Ricciarduri equation, we always take the v coordinate to be an affine coordinate. The ones where the geodesic deviation equation looks like. And actually, there's the affine coordinate is related exponentially to the Schwarzschild time in such a way, the Schwarzschild time, t equals e to the v. And so because Schwarzschild time equals e to the v, it's basically inevitable that it's going to be stationary at late times. You need actually an exponentially growing in time perturbation for that not to be the case. So at linearized order, we can actually safely impose this future boundary condition and then integrate backwards in time. And so we just end up with areas, and then 2 pi over h bar times the integral from infinity to v star of v minus v star dv d minus 2y integrals tvv. Okay? So this extra power of v minus v star just came because we integrated twice. One intuitive way to see this is that if this is v and this is our v star, and we imagine at late times the area is just going along happily being constant, and then we receive a pulse of energy, a delta function of TVV right at this instant of time, it's going to cause an instantaneous focusing, which changes the second derivative of the area. Since gravity is attractive, the second derivative is going to be negative, and therefore at the linearized level, as we go back, it's going to this is going to be a linear function now, and therefore the delta of area is going to depend on the v minus v star, because that's how long it had to run. Okay, so, but if you remember from my previous lecture, this is actually the formula for the modular Hamiltonian of the Hartle-Hawking state in the slice outside of this cut. I would write down that formula again to compare, except it's the same one, so I won't. But this means that this thing is equal to minus the modular Hamiltonian, the Hartle-Hawking modular Hamiltonian, kV star, plus a constant term, constant meaning independent of V star, so that includes a contribution, that includes A infinity, and it also includes the modular Hamiltonian associated with stuff that goes off to scribe plus.
Oh, sorry, I didn't see how can you get this area equation from your state equation?
This area equation, this thing, is what you get from integrating the linearized Reich-Hiduri equation multiple times.
But suppose there will be two integrals over the v direction.
Suppose there were two.
I think there should be two integrals over the v direction.
There are two integrals over the v direction and one integral over the transverse direction. The first integral over the v direction is what takes us from tvv to an integral. Oh, so you could have written this with two integrals like this, where there's an intermediate value of v prime that you integrate over. But what I was trying to persuade you of is that you can solve that integral and replace it with a single integral, and the effect is to add this factor.
Maybe that's more obvious if you differentiate.
Yes. So if we now differentiate this once, then we integrate by parts, and that kills this term. And then we differentiate a second time, and it kills the integral sign.
No. The second question, why you also need to take an integral over the transverse direction?
Well, we don't have to take that integral, but we certainly do if we want something involving area, because the area is integrated. Yes?
Could you say again what is the constant in your formula?
The constant has two pieces. One of them is the late time area, and the other one is that when I wrote down the formula for the modular Hamiltonian in my last lecture, it was this term plus a term k infinity, where k infinity represented the modular Hamiltonian of the Hartle-Hawking state of the piece restricted to scribe plus. So it's just the formula for it's the flux of boost, it's the flux of killing energy across scribe plus, which could have been written by an integral of the stress tensor over scribe plus if you want. But because it's independent of v star, it's not important to me.
I'm confused about why that's the Hartle-Hawking state. It's the actual physical state, whatever that is. Which, in a dynamical black hole, on scribe plus won't be the Hartle-Hawking state.
It's the modular, it's the modular Hamiltonian that comes from taking log rho of the Hartle-Hawking state, but then we view log rho as an operator and act on it on the state we actually have.
So related to that, are these expectation values, or?
Yes, so, well, I mean, they don't have to be expectation values yet, but in our applications, we'll eventually be interested only in the expectation value of the
That was an
whole.
operator equation where you had before?
I believe it should be, yes.
Is K order 1 in G?
Is K order 1? Yes. Although there's this divergence issue, but it cancels because at the end of the day, to prove that by using this formula for the area, by substituting this area in, so you see the formula for the generalized entropy, ignore all those extra terms. We're just looking at the area piece and the S out piece, and the area piece turns into K. So what this turns into at the end of the day is it turns into the relative entropy, which is just the derivative, the delta of K at V star minus the delta of S at V star. Delta means comparing to the Hartle-Hawking state. And this is the relative entropy of rho relative to the Hartle-Hawking state, where rho is the state we're interested in that we want to prove the generalized second law for. So I'm not going to try to get into too much of the details of the algebra because it should be obvious once I've related the area to the modular Hamiltonian, I will have something that looks like a free energy here. The point is that this relative entropy is monotonically decreasing under restriction, and pushing V star to the future is a form of restriction because my wedge outside has less degrees of freedom. And therefore, the fact that S rho monotonically decreases implies that S gen monotonically increases. Where the difference between decreases and increases is just this minus sign here. Okay, so that is the generalized second law for causal horizons. But it turns out there's also an analog of the generalized second law for trapping horizons. At first sight, it looks, or a modification of trapping horizons, really. At first sight, it looks like such a thing should not exist. Because I'm going to push this up. At first sight, it looks like there should be no analog of the generalized second law for the trapping horizons because this formula right here involved the specific details of how the area of the causal horizon responds teleologically to a flux of TVV as a function of V. The apparent horizon responds in a different way to fluxes of TVV in a more instantaneous way. So you could say, if I change how the horizon responds to TVV, there's no way that I'm going to get a equally nice entropy increase formula. And that would be true, except for one thing, which is that in the definition of the trapped surface, we've defined it using these thetas. And theta is all about area. And if there's one lesson we've learned from these quantum corrections, it's that when you see areas, you should replace them with quantum corrected formulas that refer to the entanglement entropy. So morally speaking, if we really want to give the trapping horizon a fair chance, then we should really define a quantum expansion. Which is capital theta, where the quantum expansion is defined as the functional derivative with respect to your slice of the generalized entropy. Where when I write this functional derivative, I want it to be understood implicitly that we're densitizing it with respect to the area element, so that this thing is defined analogously to the expansion, where it's 1 over some infinitesimal area of a d by dv, where I make sure to only modify my v in the same infinitesimal area. So I'm just pushing forwards my cut. I'm just pushing forward this slice in some small neighborhood delta A of the generalized entropy here. Okay? So this is the quantum expansion, and now it's natural to say that a future Q screen is what Busso and Engelhardt decided to call it. The Q screen, Q plus, is defined as blah, 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 all the same as this, except with theta v is equal to 0. Its quantum expansion of u is less than 0. Okay? Now, it turns out that using this modified definition, which will lead to a surface that's not in the exact same place as the original one, they also argued for a generalized second law with one given an assumption. Yes?
You probably want to put the theta v definition of
Sorry, put theta v. Subscript v. Oh, yes. I guess I did that before. Yes. Okay. Yes. Okay. So they assumed a conjecture which was already conjectured previously by a group of people mostly at Berkeley that is called the quantum focusing conjecture. And this is because the null energy condition is no longer true if you have quantum fields. So what was conjectured is that a second functional derivative of the generalized entropy is going to be less than or equal to 0 for all surfaces that all space-like codimension 2 surfaces, all surfaces that split a Cauchy slice into 2 pieces. This requirement that splits a Cauchy slice into 2 pieces is just related to the fact that we need an outside and an inside, or we can't define the entanglement entropy. So this is the quantum focusing conjecture. Because we have 2 functional derivatives, it could have a y1 and y2 at 2 different places. in which case we do the variation like this. And it's not too hard to show that if you label these surfaces as A, B, and C, the off-diagonal piece of this is actually follows from strong subadditivity. So the interesting part of this conjecture is actually when y1 equals y2, there's actually a delta function piece, and that leads to the statement of the quantum null energy condition, because the second derivative of the area piece is related to the stress tensor, and this gives a condition on the expectation value of the stress tensor that this is lower bounded by the local second derivative that I'll call S prime prime here of the entropy. I just wanted to get this far so that people have the terminology straight if they're going to ask me about this afterwards. I guess I'll begin the next lecture by saying how this quantum null energy condition is related to the other things like the generalized second law that we've discussed. But just to tie into what I've just said, they assumed the quantum focusing conjecture, which has been tested in many different field theories now, and derived that there is a generalized second law for these quantum trapping horizons, these Q screens as well. So what this means is that we now have, but this quantum focusing conjecture is a more general thing that will apply to null surfaces you draw anywhere, so I like it better. All right.